All right. Hello. Let's give this a red hot go. So I am basically testing what a streaming setup would look like by spending a little bit of time, probably the next hour or so, looking to re-implement this paper, which I saw originally, I think, on Hacker News. There's a nice write-up here on weights and biases, but effectively it is using a reinforcement learning setup, policy gradients with, I'll get into that in a second. Anyway, the goal is to recreate a target image using a number of somewhat opaque triangles stacked on top of each other and maximizing a fitness function. So we will have a red hot go at that. I am starting from nothing right now. I'm only going to do this triangle bit for the time being. We might look at this text to image thing later on. But yeah, let's get stuck into it. So I will be using the same library that they were using, which is policy gradients with parameter-based exploration. This is on GitHub by this author, whose name I'm not going to attempt to pronounce. You can check that out there, install it from Git. They got a few examples using it to create running creatures and other things like that. And there's a nice little explanation of how the algorithm works. So basically, it's an optimization algorithm when you don't have necessarily the ability to compute gradients. And it goes through a multi-step process. We'll just wait till this reloads. Actually, you can have a look at it, but it creates a number of different candidate points, determines the best direction to move in, and then updates that direction. So you might be wondering, what on earth is the point of this? We have so many deep learning ways to generate images. The idea here is that if we can get this to work, and as these authors have shown, you can start to optimize things that just don't have strictly good gradients. So the first version, I'm going to just try and replicate the triangles, but going to have a bit of a play around with other shapes, other ideas, and extend it if I get the time. But anyway, let's get stuck straight in. So I'm going to be working in this IPython notebook. I'll probably put these up somewhere at some point, but let's just get started, shall we? All right, so I got a few things installed, and you're going to have to forgive, oops, I don't call it that, it's pillow, isn't it? All right, guess I don't. So, pip install pillow. Actually, that's weird. Let me just have a little look-see. Triangles. This is off to a great start. I did install pillow. How does that work? Let's see. Got another computer over here with some docs. Oh, capitals. Yep, sick. All right, so first thing we're going to work on is actually just trying to draw some triangles. Image and image draw. For this, I'm going to use Pillow, which is a reimplementation of the Python imaging library, but you can use whatever you want. Now, that's a good question. Does that work with notebooks? Let's have a look. Oh, sick. Nice little view of my search history. Yeah, that's fine. I don't care about that. Okay, let's try that. I think it's new. We'll see. Image. Yep, cool. So if you didn't see what I did there, if you put a question mark at the end and run the cell, it prints the docs, which is handy, especially when it doesn't show the docs up properly. The mode here, I'm pretty sure, is RGBA. because we do want alpha channels in this one. The size, let's go with 256 by 256 for the minute, and we'll just leave the color by itself. Alright, so that should... Probably going to need NumPy here to do some math on the... Yeah, sick. That's an empty image. Alright, let's try drawing a triangle on that. Equals image draw. Oops. I have a Moonlander keyboard, which I'm still very much getting used to. So you'll have to forgive me if it looks odd. Yeah, let's just do a line just to make sure it all works. 0, 0 to 56. This is just draw a line straight to the middle of the image, assuming all things go to plan. And we'll set the fill to just sort of grey-ish. And then let's see what happens if we just play it again. Well, it looks like a lot of red hot nothing, doesn't it? Could it be? Alright, let's have a look. Image new. This is why you do these things as a test offline. What color to use for the image? Default is black. Modes, did I get those modes right? RGBA, yeah. Okay, it really just doesn't like to display that image. Let's just check that is the right object. Alright. I don't know. It could be this dark mode thing. I'm trying to be all clever. Let's turn that off for a second. Oh, my eyes. And I'm pretty sure there is a way to do that. Setting theme dark. Woohoo. Alright. Doesn't seem to like that. Color must be an int or a tuple. Alright. Let's take that as 2550. Next it'll tell me it wants... Okay, sick. Red, and then... Okay, cool. I don't know. It's probably defaulting to some 0 alpha channel thingo. So let's make it just this really light grey color as a starting point. And then we want to draw not a line but a polygon. So let's have a look at how we do that. What parameters it needs. Functions. So we need a polygon. We're going to use normal polygons. There is another concept in this library called regular polygons, which is like you define an enclosing circle and it'll put the points evenly around that circle, but we don't want that right now. We might try that later. It could be a cool quick alternative to the normal one. But anyway, xy is going to be equal to, alright, so it's like a list of xy coordinates. So let's go 100, 28, 128. I normally use JupyterLab. I don't really know why I used it for this, but I'm more of a Vim dude myself. Vim dude. Oh boy. Fill is equal to, let's just make it red. And we kind of want it to be somewhat transparent, because in the original article they use semi-transparent triangles to allow colors to blend a bit. We don't want an outline, we don't want a width. That should be everything we need. Sick. Alright, well, we can draw triangles. So what we probably want to do now is have a look back at the way that this works. So the algorithm optimizes a number of different triangles. The number of triangles is fixed for a certain run. And you can see here it starts off just putting triangles in random spots. So I'm just trying to find where they put the parameters. Maybe they don't have it. Okay, here. So it's a collection of n triangles. So, you know, in this case, there was 200 triangles, I think, for that Mona Lisa, which is a collection of the 3 xy points for the triangle itself and the color and the alpha. So for n triangles, we need 10 n parameters in our optimization. So it uses L2 loss for the fitness function, probably negative L2 loss. It uses ClipUp, which is an optimization algorithm available in this library, so we don't have to worry about that right now. There's a couple of things that they did in practice which make it work a little bit better. So that's more for the tricks one, but there's a bit of uniform noise, which helps in the optimization apparently, and the maximum alpha value for each triangle is limited to 0.1. So that again allows them to sort of blend triangles, as you can see here. So let's start off with a function that just takes 10n parameters and spits that into a number of different triangles, I reckon. And we'll go from there, I guess. Well, we should see what this PGP library outputs. So, okay, we give it a solution length. It'll give a list of NumPy arrays, each array being the length that we specify. So if we have, let's say, 200 triangles times 10, there'll be 2,000 elements in each one, and we're going to have to reshape that and get that all into the right mode. So we do want a function that can draw a triangle. We'll assume that the image, no, let's just do it from scratch. Okay, draw triangles. We'll take im size, and we'll default that to 256 by 256, as we have here, and we'll say params. Oh, you probably want to put that first. Good old Python. Params, and an optional image size. That'll do for now. All right, so assuming that's a NumPy array, I don't even think I have NumPy installed, so let me do that first. We'll just do it in the notebook with the old pip install NumPy. NumPy. I mean, I know it's NumPy, but NumPy definitely sounds funnier, so we'll go with that. And then we'll add it to the top here. Import NumPy as nup. All right, so let's just make a. That's an interesting question. So I'm thinking, do we use 0 to 1 coordinates and then multiply them by the image size, or do we use absolute? I think 0 to 1. That makes sense because then it's independent of the thingo. Sure. I don't know. Why not? All right. So we'll say params shaped equals params dot reshape. How do I do that in NumPy? Let's try this. Test equals np.array. Oh, let's just do zeros. And we want the size to be 1 by 200. That'll be 20 triangles, maybe. Test. Test reshape. Whoops. Surely that's the thing. Yep. So the shape is that. Let's try to think if there's going to be a problem. I like the old TensorFlow ones, which is 10 thingo none. I wonder if it'll work. We'll just work it out. No. Oh, no, it's -1. All right, good. So we want that. So what that's going to do is it's going to reshape it into however many rows it needs to make it work, and then 10 elements for each one. Now, I'm pretty sure... Man, my typing is not good with this keyboard. 20, okay. So, alright, let's start by making our new triangle. I just want to copy the text. Oh, what the flip is that? Oh, that's the URL for the thing. Didn't like that. Copy. And this one we want to be im size. What the linear keyboards? I need a second camera looking at my keyboard so people will forgive me for making such dumbass mistakes. Anyway, for triangle in shaped dot shape range, and we want that one. So we'll grab the triangle equals shaped. All right, now let's assume that we have something like this: x, y. I'll just put some spaces here because it makes it a little bit easier to. So 3 xy coordinates, and we're going to say they're all 0 to 1. And then we got R, G, B, A. And then, again, R, G, B, A will say is all 0 to 1, but we will multiply the A by 0.1. I don't know how you tell this PG, PE, lib that you only want values to be in a certain range, but we'll work that out as we go. But let's just assume we can do that for the time being, and we can always change that if we can't. So, we need to start drawing. Let's do it here. Draw equals image draw dot draw. some reason my Spotify is not working, so I am sitting here in silence just talking to myself, which makes me feel real cool. Let's say coordinates equals t 0 to 6. Could I do this? What if I just assumed it was always square? Is that lazy? Yeah, it's lazy. Come on. I'll... Just do the old update coords I times equals im size 0 I times 2, and then coords I times 2 plus 1. So I'm just updating the x and y coordinates to now be in the size of the image. So 1 should now be 256, and 0 should be 0. And then we will say image, oh no, it's draw dot polygon. I wonder if Pillow likes lists. I don't know, fuck it, we'll try. Probably shouldn't swear on this as much. Anyway, coords fill equals t everything after 6, I think, or 2, 3, 4, 5. Yep, and we'll worry about that other thing later, and then return the image. And then we do, let's just do 20, so it's 2 triangles. Yeah, whatever. Let's just see if it even works before I worry too much about putting real values in. Not unhappy. You know, I watch a lot of people write code on streams, and I think to myself, how do people make typos? Surely you can see those typos. But, yeah, clearly not. What do we got here? Color must be an int or a tuple. Is it really just that? Oh, that's going to be another thing, isn't it? Does that work? I don't know. ND array has no object list. To list, of course. I know what's a tuple, but it's going to have to... You know what? We're going to have to do this anyway. So let's just do T6, because I'm going to have to scale these anyway. I have to scale them right now. T8, and finally T9. But we'll just not worry about scaling them for a sec. Can it be... See? This is why you gotta do it. So we need 255 times that. And we want it to be an int. We'll just be lazy and just chop off whatever bits it doesn't like in the conversion. Int. God. I'm sure there is a list comprehension way to do this, but we'll do that another time. Well, let's just get some stuff working first. So, I mean, just while I'm doing something real boring, we wanted to scale this to 0.1 alpha. So we'll do that. I think I'm missing a close bracket. Yep. Good. All right. It drew 0 triangles over 0 everything. Let's just make that 1s and sick. That didn't work either. Let's just print the coordinates because that is the bit I'm least confident about. So a little bit about me, I guess. I've been running a startup for a while and got a podcast, YouTube channel, High Output AI with my mate Tom, and experimenting with some ideas around doing a bit of live coding. So that's what you're seeing now. This is something I've had in my backlog of little weekendish projects to work on for a while, so welcome. Hope you enjoy. Of course, that's not going to work because the triangle coordinates are all the same point, so the triangle has 0 size. So we're just going to do a little thing here. Oh, I don't know why I thought that would work. All right, let's make a triangle. We'll just do 1 for the minute, so it'll be 0, 0, 0, 1, 1, 1. Yeah, that'll do. 0.5, 0.25, 0.5. I'm just making these up. I don't know what it's going to look like. Boom. All right. The coordinates are 0, 0, 0, 256, 256, 256. It should theoretically work. That looks like there's something there. Let's just make that 1, actually. Right in the corner. Let's just do this. I don't think that did anything. All right, let's have a think about what I have done. It might not actually accept a NumPy array like this, so let's just go xy's equals an empty list. Whoops. In this keyboard, the equals is on the left-hand side of the keyboard at the top. I can technically rearrange it, but I'm not going to. Plus equals a little tuple, and it's a list. So I'm going to do that, and we'll do... Why don't I just do this? And for some reason it's not copying and pasting. You always got to copy twice. Copy twice, paste once. Isn't that what they say? No, nobody says that. Well, I don't know, maybe somebody says that. I do now. I hope you're really enjoying my great commentary here. I don't know if the... Oh, sick. That's what we wanted. So it's a weird sort of purpley color. Let's try some opacity. Oh, that should be 10% opacity. Let's try a slightly different color. So that's the color. It's a horrible color. Red, but we only want it to go to 10%, I guess. So 25.5. How are you ever going to get bright colors with that? Does that seem right? What did they do here? The maximal alpha value for each triangle is limited to 0.1. I could make the actual underlying thing a bit brighter. Which would then give me a bit more red in my thing. Or not. Let me just make this triangle a little bit smaller. I feel like that's almost giving me this weird brightness instead of the alpha. Let's check the docs. The fill is the color to use for the fill. That's all it says. All right. Any examples? Transparent. I don't feel like that should be so dark. Oh, unless... I don't think this is actually setting the transparency of the triangle, is it? It's painting this area with a color that is somewhat transparent to the black underneath, because I reckon if I switch this to light theme... Yeah. Okay, that's not exactly what I wanted. Maybe pillow is not the thing to use here. So I was just going to use pillow and draw some stuff on top of one another. I don't know, let's have a look. Now let's just say I did this. And we'll just do it this way so I can pretty easily get rid of them. Whatever that'll do. And we'll make it a slightly different color. Now, is that gonna put it... Oh, let me... yeah, so it's not compositing these triangles correctly. So this pillow option is not going to work. Alright, cool. Well, let's have a little look, shall we? Python draw triangles on a canvas. Let's find out what we use for this. The one that people were using was like turtle. Turtle seems bizarre to me, but maybe that's what we gotta use. Turtle. See, that seems wild. How have I not ever done this before? I mean, I know how to draw things in Matplotlib, but that's not very useful. I know how to do it in HTML with a canvas, but like, why is there not a... Let's just not use canvas. Canvas. Let's try, okay. Overlapping. That'll do. Yep, good spelling. Oh, this is gonna make for some real boring content while I look for this. Oh, cool. All right, let's have a look here. Oh. Okay, so it seems like you can do it. So what you do is you make the underlying image RGB. Oh, I actually need to make sure I change the right one. And then you set the image draw to be RGBA. Good old Stack Overflow. Oh, RGNA. All right, dope. Thank you to our Stack Overflow friend here, Matt, and the editor, David Parks. You saved my ass. All right. Good stuff. Well, we're back in business. So now, beautiful. Beautiful, beautiful, beautiful. Let's get rid of some of these thingos, these cells that we don't need. So we got our function to draw triangles on an image given some arbitrary set of things. So that's good. Now we need to probably kick into this PGP elib and see if we can't draw a triangle. So I should probably import that up the top like a normal person, not some sort of chaotic monster. Let's hope I installed that correctly. It is installed directly from Git, so if you are not used to doing that, read the instructions. So let's just take a brand spanking new example here. Yep, that's fine. Solution size here is, let's say 10 triangles. So solution size is 100. We'll just do the pop size to be, I don't know, 1 because we're real lazy. Oh, okay, cool. Has to be even, so we'll just do 2. And these comments are not valid, so let's get rid of them. And we don't even have a target image yet, but we'll do that quickly. So for our generation in range, let's just do 1 for the minute. We then get our, I hesitate to call these solutions, but anyway, the proposals for this, pgpe.ask. And then we need to here calculate fitness, but for right now we're just going to draw them, and then we need to tell it the fitness. But we won't bother with that right now, and that'll probably throw an error, so we'll just break. And here, just for the hell of it, we'll print these, or display these, I should say. For S in solution, draw, we got to do display because it's not the final return value. Draw triangles S. All right, so without a doubt, S is just going to be who knows what. So can I put any constraints on the bounds of S? That is the question. Let's find out. Because I want everything basically to be between 0 and 1. So let's have a look at the examples, maybe. Dunno. Rest. Riggin. Nice little example. Yeah. That's my dog, if you can hear him. Initial mean of the search distribution. I mean, that could be important. I mean, these current triangles are just nothing. I mean, they won't plot because they have negative thingers, and I have no idea what that does. Or if it even works. Let's maybe... Let's just say that our initial center underscore init is equal to, let's just put it smack bang in the middle, so 0.5 times np dot ones. To give it 1? Yeah, I don't know. Does that work? All right, cool. So, good. Look at that. Some initial triangles. So I just put it right in the middle. That's good enough for the time being. Now, what we need to do is we need to do a diff function. So we need a target image to begin with. So let's see, how big is old Mona Lisa here? Download that, I guess. Save that image. Sure. So I've saved that. Man, I really hope I didn't just show shit that I shouldn't have shown on my screen. But anyway. How big are you, Mona Lisa? Hopefully this is off screen now. I don't think I'm sharing this. So let me put that. I don't even know where that's saved to. Oh, there it is. We'll pop that in the folder that we are working with here, which is Linux, Ubuntu, user, home. So I'm doing this on Windows in WSL. I had an Arch set up for a while, but that was giving me some issues with my graphics card. So I got lazy and went back to Windows. But WSL's pretty good. All right, anyway, let's load our target. Equals np dot. You can read an image, can't you? Load. This is bonkers. Image dot what? Open. Dot png. Does that work? There's another image called target. Where'd I put it? Must have put it in the... Oh, it's called index. Cool. So, target. That's what we're going to try and replicate, is this lovely picture of the Mona Lisa. All right. Now, for things that I haven't done in a while, let's work out how to turn an image into a NumPy array, because then we need to do an L2 loss. There may even be a way to get NumPy to read an image. But let's find out because we're doing this other stuff in. Oh, okay. So this is real. Does NumPy know how to do that? Oh, look at that. Okay, so that's RGBA. So divided by 255. That's me trying to press shift. All right, so that gives us a target. So we might as well just do this all in one. NumPy array of that divided by 255 is our target. Oh, gosh, let's get rid of that one. All right, so that gives us something to work with. And then let's move that up above there. Then what we need to do is we need to calculate the L2 norm of these. So the L2 norm is the square root of the summed square of the differences. So given that we're working in NumPy, we can probably just do this without too much worry. Is that going to be an issue? So what I'm thinking is it going to be a problem that this is RGBA and this is RGB? But we'll find out. Let's see what we get out of this. All right. So let's just check the shape of this, because we kind of just want to drop the alpha channel. Okay, cool. So target equals that. All of them, but only up to that. I think that's going to work. Yep, cool. All right, so we'll just drop that alpha channel. No worries. And, oops, I don't know why I bothered saving. Anyway, so now we've got this candidate 10, and the diff is equal to target minus C. Oh, this one's also going to be in. Hello, Bob. Target minus C. Dogs, eh? How's that going to work? Operands could not be broadcast together with two different shapes because the Mona Lisa is not that size. So we are going to use our imsize thingo. Imsize equals, because this Mona Lisa image is, oh, I guess we should just do target dot shape. First two of those. How about that? Good. All right. So those are our two L2s. And now we fitness equals this. And then plus equals diff. And so the closer these are together, the lower this number is going to be. And we want to maximize the fitness. So we're going to make that a negative fitness. And then we're going to say fitness. Cool. Oh, let's just see if that worked. All right, cool. So what we're going to do here is we're going to print Yeah, let's just print it because I'm lazy. The mean of the fitness. Oh, yeah. Cool. And we're now going to go some more steps and see if it makes a difference. So 3642. Not really. So what I need to do here? Let's try actually just make a slightly bigger population size. Also, we can't really expect it to be that good with 10 triangles. So how many did they do? They did 2,000 steps. Okay, I can work with that. And 2,000 iterations, 200 triangles. So let's work with that. So 2,000 steps and 200 triangles. So 10 times 200. Let's just be explicit there. And the center in it is 10 times 200. And we're going with the pop size of 20. I don't know what they used as their pop size, but 20 will do. And then let's just do this rather than store this. Let's just, rather than print it, let's just do that. And I probably want matplotlib so that I can plot f over time and we can see how this fitness changed. This has taken a while. I should have installed TDQM or whatever it's called. I think that's what it's called. TDQM. Yep. TQDM. There you go. Always get that wrong. So while that's running, if you haven't seen this before, it's a little library that takes a range statement or pretty much anything else and turns it into a little progress bar. And it works nicely in notebooks too, if you get it set up correctly, which I very rarely do. Anyway, not that important. Maybe 2,000 was a few too many. Anyway, doesn't matter. We'll wait and see. So, if this works or makes any difference, that was pretty quick. As you can see, this is pretty powerful little algorithm. And hopefully we get something interesting out the end, but we'll see. Are there any other steps that I need to do when I'm done? Yeah, that would have been a good idea to just print every now and then, but let's go. So loss started at that and ended at that. Oh, wow. Okay, so let's draw. We'll just pick a random one out of the... Oh boy, this right-click thing is really annoying me. Let's just draw one of the last triangles out of there and see what it looks like. Look. It's not red hot the best, but let me just pop old Moni Lizzie next to it. I think I might have actually fucked up the square thingo. In terms of just blanket colors, not too bad. What else might I have messed up here? S is the right size, right? Oh, S is 100. Why is that? Did I not start this again? Okay. Anyway, let's do FF%. Oh. So one of the great things about having an unlabeled keyboard is that it's really hard to know where all the symbols are. I did not want to do F. If gen is that, so let's do that and that and that. And let's see if that made a difference. 10 by 200, 2000. That's what it should be, right? I mean, look, if that really is 100, which is 10 triangles, and that's an estimate for the Mona Lisa after 10 triangles, yeah, not too bad. Not too bad. Actually, you know what I'm going to do? I'm going to stop this, and I'm also going to just draw the very last triangle at the same time, and we can watch how it changes. And because anyway, we'll make this prettier later. Coding rule 101, everything doesn't have to be pretty. The first time, especially when we are doing this live to no one. All right. So, as expected, starts as a bunch of triangles in the middle. That looks like a lot more triangles than we had in the other one. Changing. The loss went down a little bit, I guess. Starting to spread out, definitely, which makes sense. I mean, most of the Mona Lisa is not white. Spreading out a bit more. This is quite cool. This was surprisingly easy. When did I start this? About an hour ago. Not too bad for an hour's work. I might, look, if I get good output at the end, I'll put this up somewhere, probably on YouTube. This obviously wasn't live, but we'll pick this up another time, I think. I'm not going to put any editing in here, so apologies for the dog noise in the middle. I'll work out as well how to make this a little bit prettier. And then next time we can start playing with some other shapes and some other ideas, and like really start to see where this algorithm can be useful. So while that's running, anyway, they have a lot of different examples here with different number of triangles and things like that, different pictures. And as you can see, like, it approximates okay, but it's never going to be the most amazing thing in the world. But the idea here is that, you know, if you were given a list of 10 times n coordinates, you really can't compute the gradient on that. You can't say, like, how do I move these triangles such that the L2 loss goes down, which is where this fitness algorithm, or I mean this PGPE, policy gradient with parameter-based exploration method really comes in handy. So what it does is it takes your solution, it picks some random points around that solution, picks mirrored points at the other side, and then uses the 3 points, the current center, A and B, to compute a bunch of gradients of the fitness function. It then computes the best, or it computes how much fitness you would gain along each of these vectors, takes the weighted average, and then moves the center in that direction. So you'll see it moves the center up to here. And this means that as long as you can calculate a fitness function, you can run this optimization. So if you've ever done anything in the world of like genetic algorithms and so on, this will feel pretty familiar. But there's some optimizations here around sort of ClipUp and some of the way that it works that makes this a little bit more powerful. Let's check in here. All right. Mona Lisa, how we doing? Well, the image is certainly filling out. I struggle to believe that that is a 0.06 L2. But we'll wait and see. I should have printed how many iterations it's done. 50 times however many this is, I guess. Anyway, we'll keep an eye on that, and we'll see where it gets to. But this was surprisingly easy. I thought... there you go. Didn't know it did that. Trim the outputs. You can start to see that it is sort of matching the average color of this picture of the Mona Lisa a little bit here. I will work out how to do this in a way that's not just print, but it's a problem for another day. This has worked out pretty well thus far. And how long do I have? I got probably another 10 minutes before I have to go do something else, so we'll see where this gets to. I mean, it is vaguely starting to take shape of darker space in the middle. This could just be me projecting my own desires onto how this image turns out, but we'll see. Kind of cool for an hour's work. Yeah. I wonder what other cool stuff we can do with this. Put some more constraints on it. See how we can get creative. I mean, obviously, if you've been doing AI for a while, especially in the image space, you know that L2 is, it's okay, but it's not the best metric in the whole world. You tend to get, it's not going to matter here because it's just triangles. You tend to get kind of blurry images and things like that when you get to the more fine-grained level. But you can imagine, given that, we'll just scroll up here, the way that this algorithm works is it'll give you some proposals. You do whatever you need to do to calculate the fitness function, and then you just tell it the results. You can imagine, rather than draw the triangles and calculate the L2, if you didn't care about how fast this went, you could generate the images, post them to a website, allow 48 hours for people to vote on their favorite, and then use the voted scores as the fitness here. And that's what makes this really powerful, is that it's a really flexible algorithm to be able to optimize things that are traditionally quite hard to optimize. I've generated these images within Python just because it's quick for this proof of concept. But again, you could pass that off to an external service. You could use this as input parameters to a robotic control arm doing something in the real world. This as a form of reinforcement learning, this is not too bad a starting point. Okay, I think that was 2,000 generations. Does that look like the Mona Lisa? No, probably not. Let me just double check here. Let's do a couple more things before we have to disappear. So let's print the generation and the fitness. Let's do it every 100. Pop size of 20. Was there any information here about the population size? Hey, pop-up. That's not nice. It's very loud. Oh, by the way, there are examples of this on Google Colab, which I didn't have a look at, but they may reveal some secrets to us. What do I need to square root this loss? Maybe. I guess it doesn't really matter if they're all scaled the same, does it? I guess the mean. I guess again the mean and the sum, it doesn't really matter. Does this work? I don't know. No. But I do need to do something. And then I need to I did square rooted. Square the elements, square root the total. I think. Let's find out. I don't actually know if it really matters. No, I guess you don't. Alright, cool. Well, that's fine. To just scale it anyway. So, I don't know. What else could we test out here to see if we can get a slightly better or slightly closer image? I do like that. That's cool. Obviously, the center initialization thing is one. I don't know what the pop size should be. What does theirs look like early on? Yeah. Well, let's have a look here. What other options do we have? Optimizer, clip up. What's the default optimizer? One thing about this is the docs are kind of just the examples directory, so that's always fun. Let's have a look at this reinforcement learning example. Oh, this was a fun one. Cart pole problems in the gym. So they have a pretty big pop size. Actually, let's just have a look at the end now of the vast array of different triangles that we get. I mean, not triangles, examples. Display. So, look, they all look kind of similar. What do I take away from that? Not much, really. It just feels like it needs more time, which could mean that some of these parameters are too small. Let's try this. That is definitely going to make it slower, so we'll just live with that. And see what happens. Yeah, that should be fine. All right, cool. All right, now it'll print 20 odd images along the way. That got way bigger. Oh, because I used the sum instead of the mean. Shouldn't matter. And it's printing the generation now, so we should be able to keep better track of it. And once this is finished, we will call this a day and say farewell till next time. But we'll see where this one ends up. I guess at some point we should try a different image as well. Maybe. Yeah, it definitely feels slower. I guess I did make the population size 5 times bigger. So the way the population works is that's how many samples it takes around the center point in terms of determining the next direction. Should, in theory, give it a smoother answer as to which way to go, but we'll see. We'll see if it ends up better. There's a whole bunch of learning rate parameters and all this other sort of stuff that we can mess around with. Some pretty good examples in here. Anyway, check this out if you haven't already. PGPE-lib, great open source project. It was created ages ago. This paper, or at least this notebook, was last updated in the 25th of May by Soumik Rakshit. Hope I pronounced your name correctly. But the paper is also available on arXiv if you want to have a look. And yeah, let's just run this out and see where we get to. And if you notice anything I've done wrong here, because there's a potential chance that I have done something incorrectly, do let me know. I do wonder how we can stop the parameters from going outside of a range that we care about. Because obviously, you know, if you get negatives and things like that, who knows what that's going to do. With the images, with the triangle coordinates, I mean, it'll just plot them outside the image, but with the colors, I don't know what happens. Maybe it wraps around, maybe, who knows? Who knows? So, What I did find interesting in this example is they have a positive fitness function. And I don't know how they do that. I mean, I guess they could do the mean and they could do 1 minus. But yeah, I don't know. I don't know. That makes more sense, actually. Anyway, whatever. Putting a negative sign in the front will do the same thing. You can see here that some of these, like, they are a bit meh. There's not really many examples here with more than 200 triangles, so who knows what that would turn out like. And I haven't even touched this text to image process. I might do that next time, who knows. I'd kind of rather play around with different drawing methods just to really see where we can take that. You know, what if we didn't use triangles? What if we use circles or regular polygons or anything else? Because personally, I think that's quite an interesting thing to work on. 300 out of 2,000. Ooh, we're going to be here for a while. All right, you know what? I'm going to let this keep recording, but I am just going to cut from right here to when it's done, and then we'll wrap up this video because it's going to be real boring if you sit here and watch iterations tick over. I would assume. You know what? I'm going to try something different. Scratch that. Stop. I don't reckon this is the problem. I reckon we'd be better off doing this. And I'm going to change that back to the mean. It's weird to do the RGB channel separately, but anyway, let's worry about that another time. Yeah. Smaller population, more steps. That kind of feels like the right way to go. Because I don't feel like the problem was that there wasn't a good gradient approximation. I feel like it was just sort of getting there, but didn't quite get there yet. So we'll see where we get with this one. It's cool that the triangles do get bigger and start to fill out the space and thing, though. It's a cool little algorithm. One thing I don't have is they mentioned that they fill the canvas with uniform noise, maybe? Uniform distribution noise, so that this is equal to modeling the uncertainty of parts not covered with a max entropy assumption. Now, that could make a huge difference, and I don't know. I guess we can try that. That doesn't seem like the hardest thing in the world to do. Maybe? I don't know. I can initialize a NumPy array with noise and then work out how to turn that back into an image. Maybe that's something for next time. I do think my initial point could use some work. I mean, you can see here this is much more diverse than what they have. Oh, wait, sorry. Theirs is much more diverse in sort of color and overlappingness than me, who just stuck everything in the middle as a starting point. That may end up making it sad. I also genuinely think there must be some way to limit the parameter space. I gotta know. Let's have a look and see if we can work out how it generates its candidates. Because if it's like -1 to 1 or something, we can obviously just scale those. So, PGPE solutions. All right. Population max. Okay. Random state. Yep, that's fine. Ask. Return. Increase population. I don't know what that... Anyway, let's have a look. Number directions. Noise. Scaled noise. Solution is the center plus the scaled noise. The mirror is this... Yeah, okay, that makes sense. Random... I mean, it doesn't appear to have much in the way of clipping or limits or any of that sort of stuff, so maybe I'm just thinking too much and this is the way to go. I mean, this is... Ooh! I mean, it's starting to lighten up. We're starting to get some darkness around the hair. I think this was the winner. Let's wait and see. And then I really should sign off because I do need to take my little pup for a walk. Yeah, this definitely seems like the winner. Very cool. I'm going to put this video up and we'll see if people like it. I'll put it up on my personal channel. I'm going to try and do these live at some point. Maybe once a week to start with. This is pretty fun, pretty easy. And it's a good little starting project. Now, obviously, I mean, one thing in here is I am only printing one of the solutions. There is a whole population of solutions here. What I probably should do at the end is I get the center point and plot that as opposed to the center point plus noise. But anyway, not bad for a first go. Mona Lisa from Triangles. Cool. I'll throw this notebook up somewhere. A GitHub or something. I don't know. There might be a better notebook hosting solution. But you can have a look at it. You can play around with it. And I'll keep playing around with it next time, I would say. Oh, look at this. Leonardo da Vinci would be proud of this work, for sure. Maybe this is what he was trying to do all along. I should be able to do this faster too. So like the specs on my machine are not crap. Obviously you can't see this window, which is good because it probably has revealing information. But what have we got on this computer? We got 64 gig of RAM, Ryzen 5, 3.7 gigahertz, and what GPU do I have? I think I got a 3080 Ti as well. So we should, in theory, be able to find a way to compute these in parallel. I mean, that's another good thing about this algorithm. 3080 Ti. Each fitness calculation doesn't depend on anything else. So it's an independent set from the parameters. So this is one of those sort of really easy to parallelize. What a funny word, parallelize algorithms, because you can compute each one of them separately. And I'm sure there are examples in the thing about how to do that. All right, look at this. Come on. Come on. How good is this? This deserves a tweet. Hopefully this is interesting content. I'm not actually going to cut any video out of this in the end. Hour 20. You can watch it. It does look as if maybe I should zoom the screen a little bit more, but for the purposes of seeing pictures, this is actually not too bad. And what I'll do offline is I will run one of these with an obscene amount of iterations, like 10 times this many, and just see where it gets to. But that's a question for offline. I'll make that part of the thumbnail. And we're coming up to the end here. 4,800. How many did I say? Did I say 5,000? Oh, I gotta find a better way to do that too. Yep, 5,000. $4,900. Oh, it's probably not going to print the very last one, is it? All right, well, let's just do that very last, print the center solution, and be on our merry way. So we'll take this and, oh my gosh, pgpe.center, maybe? I don't know. We'll see. Display triangles, dot center. There you go. That's the center. That's the Mona Lisa, or as best we can approximate with 200 triangles and 5,000 iterations. I hope you found this cool. This was worth it for me, and who knows? Catch you next time. Bye.